Okay, let me share the screen. Yeah, you're able to see my screen, correct?
Yes, sir.
Yes, sir.
Great. Yeah. So in the last class, we have looked at the safety factors in SN curve. We have looked at the safety factor in stress and safety factor in life. All right. So far, whatever, and we have also solved the problem. And so far, whatever we have looked at is only for fully reversed loading, the SN curve and then the correction factors, whatever we have talked about and so on, are under the assumption that the loading is fully reversed, which means the mean stress is zero. All right. Now, in today's class, we will look at what happens when you have non-zero mean stress. That means if the loading is not fully reversed, but something else, and if you have a non-zero mean stress, what happens? So as you increase the mean stress, that means over and above your fluctuating load, there is some constant load that is acting on the component, right? That is how you should look at the concept of having a mean stress. So that means if it is positive mean stress, that means if the mean stress is tensile in nature, then that is going to be detrimental to the component. Why? Because it is tensile in nature, that itself will add some uh, fuel to a growing crack, right? And hence, if when it is zero and when it is some value positive, then that is going to be a detrimental. As a result, the fatigue life decreases with increase in mean stress for a given stress amplitude. That is what we are saying. So suppose if you have this red curve, sigma m3 is your stress strain curve. Let us say sigma m3 is 0. All right. As you increase mean stress to be some finite value, sigma m2, then on the SN curve, the curve looks like that. That means for the same stress amplitude, with a mean stress, the life will be much less compared to without mean stress. And if the magnitude of the mean stress, if you continue to increase, then the life decreases. For example, if I take stress amplitude here, corresponding to that life, if the mean stress is sigma m1, then the life will be this much. If the mean stress is sigma m2, then the life will be that much. And if the mean stress is sigma m3, that life that much. Meaning sigma m1 is greater than m2 greater than m3. As you increase the mean stress, in all these cases, we are saying that the mean stress is positive. That means the tensile state of mean stress. That is when the situation becomes more severe and the life reduces. Okay. Now, let us try to understand this. Suppose if I would plot my mean stress here, all right, and the alternating stress on the y-axis, sigma A, stress amplitude on the y-axis, mean stress on the x-axis, then when you have your stress amplitude 0, what is the meaning of that? What is the meaning of stress amplitude being 0?
Static load.
Static load. When you have static load, when will the material break?
Yield point or ultimate.
Ultimate tensile point. So the sigma F here corresponds to when the stress amplitude is 0, this point corresponds to ultimate tensile strength of the material, right? Now, if the mean stress is 0, right, for a given, so what am I saying here? So if you look at this particular graph, okay, let us say I take a particular life here. Are you able to see that? For a given life, as my at sigma m1, my at that stress, at that particular life, the critical stress amplitude is that. That means that is corresponding to the failure stress amplitude if your my mean stress is that. At the same life, if you increase the mean stress, my stress amplitude at which the failure happens reduces. If you further increase the mean stress, it will further reduce. So as you increase the mean stress, the stress amplitude at which the failure happens is reducing. And if you connect all those points, so for example, if you in this graph, if I take these 3 points, if I plot these 3 points on this graph, This line corresponds to a particular life. Is that clear or not?
This red
Whatever I
line is
said, sorry.
this red line what you have plotted, alternating stress versus mean stress.
So
So that
let
is for
me,
one particular number of cycles. That's what you're
correct,
saying,
correct.
right?
Yeah, exactly. 1 minute. I am going to share. Yeah. So I will explain it on the, because when I write it, probably you will see it better. Okay. You are able to see my screen now? Yeah.
Yes, sir.
My iPad, you are able to see, right? Hmm.
Yes, sir.
So today is 24. 25. So what I'm saying is, let us say you have an SN diagram. In the SN diagram, let us say this is 10 power 3 cycles, this is 10 power 6 cycles, right? We said at 10 power 3 cycles, it is 0.9 times SUT. If it is steel, let us say this is our 10 power 6 cycles, then it is 0.5 times SUT, right? Then if it is a log plot, then it will be a straight line. Do you agree? Maybe I will change it. So this is the scenario when sigma m is 0. This S is also nothing but stress amplitude. Either S or sigma A, both of them can be used interchangeably. These values 0.9 SUT and 0.5 SUT correspond to sigma m equal to 0. Is that clear?
Yes, sir.
Yeah. If you are doing a test where mean stress is not 0, let us say mean stress sigma m greater than 0. Then what happens? This line might actually become like that. Okay. This is sigma m greater than 0. That means as we increase sigma m, that is nothing but mean stress, the life decreases. Is that clear? Why does it happen? If you look at stress time diagram, this is, let us say, this is stress and time. If this is 0, right? This is your sigma A and this is your sigma m is equal to 0. But let us say if you have non-zero mean stress, so let us say repeated loading, then my mean stress will be, that is my sigma m greater than 0. So the black line there, so I should have used different colors. 1 minute. Okay, now you understand, right? The black line above corresponds to sigma m greater than 0 and blue line is sigma m equal to 0. Now you will see that if you have a crack, of course it is subjected to a time varying load. but on the top of that, always the system is experiencing this mean stress. That means there is a positive mean stress. That means some tensile load is there, and hence that is going to be much more detrimental. And as a result, your life will reduce. So if you would, the diagram that I have shown in the slides, if you plot stress versus life, right? And I have, this is sigma m1. Let us say this is sigma m1, sigma m2, and this is sigma m3. Sigma m1 is greater than, sigma m2 is greater than sigma m3. Why is that way? Because as you increase the mean stress, all of them are greater than 0. Oh, sorry, greater than 0. Sorry. Right? All of them are positive. Now, if I take a particular life, what does this represent? Let us say this is n1 number of cycles. That means if the component fails at n1 cycles, that implies that corresponds to, this is the sigma A1, this is sigma A2, and that is sigma A3. If I would plot a graph which is x-axis is sigma m, y-axis is sigma A, let us say sigma A3, this will be my sigma A3, comma, sigma M3. This will be my sigma A2, sigma M2, and that will be my sigma A1, sigma M1. And they need not be on a straight line, but you will see at a later stage that they are reasonably on a straight line. So this represents what? This represents a failure line that gives a life of n1 cycles for various sigma m, sigma A combinations. Is that clear? Are there any questions here, or is it clear or not?
Clear.
This line
Yes,
is
sir.
straight.
Yes, Srikanth.
This line is straight because N1 is constant because of that.
So this line is giving you n1 number of cycles. If n1 is the life, corresponding to that life, these are the combination of stresses that gives you failure at n1 number of cycles. So this diagram is also called constant life diagram. Okay. So now I am going a little ahead of that. So let us say this is sigma m, sigma A. You have taken any 3 points, and then I could actually, let us say if that is so, let us say these are the three or these are the 3 points, let us say. If those are the 3 points, I draw a line connecting those 3 points, and assuming that they fall exactly on the same straight line, it need not be, but for the sake of argument, then this line extends and hits x-axis at that point. That line extends and hits y-axis at that point. Okay? If, what can I say now? Let us say on the x-axis, wherever it hits, sigma m critical, and y-axis, I am calling it sigma A critical. Then what can I write the equation of this line? What is the equation of this line?
Y equal to mx plus c, something like that.
There is another form of the equation if I know x-intercept and y-intercept, x by a plus y by b equal to 1. Do you remember this?
Yes.
Yes, sir.
A is x-intercept, b is y-intercept. So what can I write? Sigma a by sigma ac plus sigma m by sigma mc equal to 1. Right? Yes or no? X-axis is sigma m, x-intercept is sigma mc, x by b, x by a, plus y-axis is sigma a, y-intercept is sigma ac. To make it more realistic, we know that because on the x-axis sigma a equal to 0, that means this should actually be sigma ut or sut. And here for that particular number of cycles is n. Nf is the number of cycles. Corresponding to that, this will be what? My SF. When mean stress is 0, the failure corresponding to those number of cycles is SF. That means stress amplitude. So now I can rewrite this as sigma m by SUT plus sigma a by SF equal to 1. Can I write that? Yeah?
Yes, sir.
Yes.
So any point if my stress sigma m sigma a combinations are within this boundary, that means if it is the data point is here, that means the material is experiencing a combination of mean stress and alternating stress to be somewhere here, then this is safe. If it is outside that, then it is unsafe. This is safe, this is unsafe. So I can write if my sigma m by SUT plus sigma a by SF is less than 1, then it is safe. Is greater than 1, this is unsafe. Equal to 1, failing. Right? If you want to add factor of safety to this, then how do you solve? Sigma m by SUT plus sigma a by SF is equal to 1 by factor of safety. I don't want to use n because n is used for number of cycles. FOS I am using factor of safety. That is how you write this equation. And this equation is popularly known as Goodman line. You heard of Goodman diagram, isn't it?
Yes, sir.
That is our Goodman diagram. Okay?
Sir, only one small question.
Yeah.
When I say that 1 by factor of safety, so my Goodman line will be coming down, right? Like
No. You have to say if your factor of safety is equal to 1, that is what it will be. If it is greater than 1, then it will come this side, right?
yes.
You are adding factor of safety, no? It is coming inside. Yeah?
Yeah.
You can simply see this as multiply everything with factor of safety, then sigma m into FOS by SUT plus sigma a into FOS into SF is equal to 1. FOS is greater than 1. That means we are talking about sigma m, whatever number, into FOS. So that means I am making it move that way. Right? Actual value is this, but I am making it move it that way. Or it is another way, I can actually move it this way. Right? Yes.
Correct.
Or I can also say that sigma m by SUT by FOS plus sigma a by SF by FOS. Correct? So SUT by FOS will bring it this way. This guy will bring it that way. So it may, depending upon that, the equation now becomes that. Do you see that?
Got it.
Any other questions? So, as I said, it's a constant life diagram. When I plot sigma m, you are able to see my slides now, I hope.
Yes, sir.
Yeah. So sigma m is the mean stress, sigma a is the stress amplitude. Although I have drawn it to be a nice straight line, in reality, they won't be straight line. This will be like something like that. See, you can see for different number of cycles, NF is equal to 10 power 4 cycles, this is the line or a curve, and 10 power 5 cycles like that. This is for axial loading. If you do axial loading on your aluminum sample, this is the data that people have given. And we in this, we only are talking about positive mean stress. What happens when you have a negative mean stress? You simply extend the line that way with a straight line. So on the right hand side, again sigma mean stress. Here, if you carefully observe, it is mean stress and stress amplitude. Now, if I normalize my mean stress and stress amplitude with respect to corresponding ultimate strength, so ultimate strength is this, and sigma AR is the stress amplitude for failure at those many number of cycles with zero mean stress. That point has come out to be this one. So then these are the data points. The data point collapse. So instead of in this plot, if I say sigma m is this and sigma a is that, then sigma a, if I am normalizing, instead of here I have given the complete without normalization, but when I normalize, all these points will converge to one value. All right, then I can write my equation sigma a by sigma ar. I have written SF plus sigma m by SUT. Instead of FB, I have written SUT equal to 1. This is one equation, or you can also represent that using this parabola. This parabola is called Gerber's parabola. So that means on the x-axis it is still linear, on the x-axis it will be, because it's a parabola about y-axis, so sigma m by sigma u whole square is equal to 1 and sigma a by sigma ar, or in our case sigma a by SF plus sigma m by SUT whole square is equal to 1 is the representation for Gerber's parabola. And this one is what we call Goodman line. Okay. So again, we are reiterating the effect of mean stress. When the mean stress is not zero, one needs to develop different SN curves for different sigma mean values. So there are several failure theories, of which Goodman diagram is the most used. Or in fact, not the original Goodman, but the modified Goodman diagram that takes into account of the experimental data. And that actually is going to be our representation of the modified Goodman theory itself is what we call Goodman diagram. So let us say sigma m and sigma a. Here I should have written SF. Don't worry about SE means endurance limit, but it can be interchangeably used as SF. And this is sigma y. If I am observing sigma y on both sides, if it is sigma y is the yield strength of the material, I am also identifying sigma y on this same distance. If I connect my SF with sigma y, then that line is what we call Soderberg line, very conservative one. But then later Goodman said, okay, on the x-axis, although you are saying failure, when zero mean stress is there, failure is not for a brittle material, it is not because of the yielding, but because of the fracture. That is why you should not take yield, but you should take ultimate tensile strength. And that is your modified Goodman diagram. That is what we have seen in the previous discussion. And instead of connecting with a straight line, if you connect it with a parabola, then that becomes your Gerber's parabola. Okay. And this is also people take into account of the sigma FB, which basically has to take care of Bridgman correction, which we are not going to worry about. Don't worry about this line at this point of time. Let us focus only on modified Goodman line and Gerber's parabola. Right? So this is the Soderberg equation because it's a straight line connecting these two. So instead of sigma m denominator being sigma ut, it will be sigma y. Everything else remains same. Okay. So these are the failure theories when you have a material with what you call subjected to a non-zero mean stress. Are there any questions here?
No,
Okay.
sir.
Yeah. So what happens when you have compressive mean stress? So compressive mean stress is beneficial. So if you have tensile mean stress, zero mean stress, if it is tension, the life reduces. If it is compression, life increases because it will delay the propagation of the crack. Okay, that's a good thing. However, when we are dealing with compressive mean stress, what we will design it to be, we will not add the benefits that are coming due to compressive mean stress. Rather, we consider the scenario equivalent to mean stress being zero. Okay, that means our design is based on mean stress is equal to zero scenario. We will not really account for the benefits given by the compressive mean stress. So normally the compressive mean stress adds beneficial things. However, designers consider zero mean stress to do the calculations, making the process more conservative, as I mentioned just now. That means the curve will not continue to grow like that, but it will become a horizontal line. That means with increase in compressive mean stress, normally the curve should go down like this, but we will not let it go down like that. It will maintain constant. So now let us look at this problem. In the last class, we have looked at it. The steel specimen mentioned in the below tabulated data. This data is for zero mean stress, subjected to cyclic loading with a tensile mean stress of 200 MPa. Now it is subjected to cyclic loading with a tensile mean stress of 200 MPa. That means sigma m is equal to 200 MPa. And from this you get a SN curve, which is done using zero mean stress. Okay. What is the life expected if the stress amplitude is 450 MPa? Can you please go ahead and start thinking about how we want to solve this problem? This I will give you time. Please think about it and then come up with a solution. I am giving you time 5 to 10 minutes. So this is the data that we have seen in the last class. You probably have noted down A and B. This is done for zero mean stress. Please keep that in mind.
Professor, is it 8.9 into 10 power 4 cycles, the life?
Okay, let that be the answer, and then let others also comment. Yeah. For this data, what is the value of A and B? S is equal to A n power B is there, no? What is the value of A and B that you have taken?
1584.2 A
Yes.
and B is 0.094.
Okay.
Negative, right?
Yeah,
Yeah, it should be negative.
Yes.
Yeah, minus
Yes.
0.094.
Yeah. One 1540 and
1584.2
1584.2.
A.
okay, with the fitted line, right?
Yes, trend line. Yeah.
Okay, you will tell me. I'll let me. I hope. So that's the data for the given table. That's given at sigma m equal to 0. S is equal to A n to the power B. That is equal to S is equal to A is 1538 times n to the power minus 0.094.
94. A is 1584.
1584 times n power minus 0.094. So what he is asking is, what is the life expected if the stress amplitude is 450 MPa and mean stress is 200 MPa? What he is asking is the following. Let us say in this graph, sigma m and sigma a. In this graph, this point is known, SUT. Is this point known or not? On this graph, one point is known. Do you agree or not?
Yes, sir.
In the Goodman diagram. And now what he wants is, for the combination of sigma m and sigma a to be 200 and 450, let us say this is that point. That is 250 comma 450. Okay, maybe let this be that point. This is 250 and that is 450. Okay. Because Goodman diagram is a straight line, how many points you will need on that line? Two.
Two.
Only 2 points. So I know these 2 points. Now I can draw a line. Yes or no?
Yes.
That is my sigma a. What is the beauty of this line? The beauty of this line is that the life given, this is what is this name of this line? Goodman line, or also known as constant life diagram. What is the meaning of that? All the points on this line will have same life. Do you agree or not?
Yes.
Which means this point and this point will have same life or not? So this, let us say point 1, where actual scenario of 200 ampere 450 ampere combination is there. Let us say this is point 2, right? And maybe I will name it differently. Let us say O, A, C, and let us call this point B. Okay. Since A, B, C is a constant lifeline, right? The life given by point stress state corresponding to points B and A will be the same. That is the argument. All of you are convinced with this argument or not? That's how we drew this line, isn't it?
Yes, sir.
Yeah. Now let us look at A, point A. What is the scenario here? This corresponds to sigma m equal to 0. Mean stress is 0, isn't it?
Yeah.
Yes, sir.
Yeah. But we don't know what is, let us call this as SF, but we don't know what SF is, right? But we know at a 0 mean stress, this material is governed by this law, because that is given by that trend. And hence, therefore, SF is equal to, so we can apply S is equal to 1584 to the power n minus 0.094 to A. Can I do that? You understand why am I applying this formula there? Because this formula is suitable when mean stress is equal to 0 for that material. It is the same material and this point corresponds to that. And hence, the stress state at this point should satisfy this line equation, isn't it?
Yes, sir.
Yeah. So I am plugging in. So S is 450. What, I don't know what it is. I need to find out. Huh? So I need to find out the life, right? What will be this point, SF? Can I find out SF? I need to know, in order to find the life, I need to know what SF is, isn't it? Because then I can plug in SF and then get M. But what is SF?
We can use the equation of line to get
Intercept
SF.
Exactly.
equation we
Can
can
I
use.
get the equation of this line or not?
Yes, sir.
What is the equation of this line?
Sigma,
Y,
Sigma
so
A
Y,
by
so
yes.
sigma A, that is Y, minus 450, that is Y1. Or I can take this point also, sigma A minus 0, that is this, is equal to M. M is what? Y2 minus Y1. So this is Y1, this is Y2. Y2 minus Y1 means 450 divided by X2 minus X1. X2 is 250 minus X1 is how much? 1172 into sigma M minus 250.
Professor, X2 is 200, right? The given is 200, I think.
200, okay, sorry. So let me write down that clearly. I hope all of you are following. If there is anyone who is not following how am I writing these equations, you have to be very clear. So this is an equation of a line. X is sigma M, Y is sigma A, Y minus, I am calling this as 0.1. This is 1172. And yes, sigma A in this point is, so this point is 1172 comma 0. That is that point. Y minus Y1, that is equal to M. M is Y2 minus Y1, that is 450 divided by X2 minus X1 is 200 minus 1172 into X is sigma M minus X1 is 1172. Agreed? That is the equation of that line. So the equation of that line, now if I plug in this point, what is this point? 0 comma SF. Right? A sigma m is 0, a sigma is SF. So SF is equal to, basically I'm plugging in this equation. SF is equal to 450 divided by minus 972 into sigma m is 0 divided by, so that means minus 1172. That will be my SF. What is that value? $450 star 1172 divided by 972. That will be 542.6 MPa. So this guy is now 542.6. Now having found that value, now I need to plug in, so that therefore,
Professor, in this,
Instead
can we
of
use
this,
directly the Goodman equation?
yeah, I am plugging in the Goodman equation, no?
I mean, instead of doing this way, can we use that sigma m by I mean,
If
that
you,
relation?
yeah, but we don't know what is SF, right?
So SF only
You
you
can
are
also do
plugging.
that.
The
Sir,
same value
sigma m is equal to 0, then is equal to 1, right? So
equal to 1.
we can found the SF from directly, right?
So what is that? So let us do that also. Sigma m by SUT plus sigma a by SF equal to 1, right?
Yes, sir.
So you can plug in this equation. Sigma m is 200 by SUT is how much? 1172 plus sigma a by 450 by SF equal to 1. Isn't it?
Yes, sir.
Yeah. So what will that be? 1
Same.
minus 200 by 1172, 450 by that will be my SF, isn't it?
Yes, yes, sir.
That is what that is exactly what it will be.
Same numbers.
Same, sir. We got the
Yeah.
same number.
You can do that or this, both of them are same. Therefore, the number of cycles of life corresponding to sigma m comma sigma a is equal to 0 comma 542.6 is 542.6 is equal to 1584 times NF minus 0.094. Therefore, NF is equal to 542.6 divided by 1584 whole to the power minus 1 by 0.094. What is that value?
89,200.
Yeah,
How much?
89,191. 89,191.
89,191 cycles. Now you will say that since 0 comma 542.6, that is point A, and point B, that is 200 comma 450, are on the same lifeline, the number of cycles for the state sigma m comma sigma a is equal to 200 comma 450 will also be 89,191 cycles. That is how you arrive at. Is that clear?
Yes, sir.
Any questions there? Is it clear to everyone? What I'm observing is that I've looked at you must have seen your marks. It appears several people are not able to follow because I have seen blank answer scripts given to me in the exam. Right? That is a little unsettling. If you are not able to follow, you have to tell me, because otherwise you will have trouble if it is blank sheet, which basically means that there is absolutely nothing that was discussed in the class gone into your system. Yeah. And that later in the final exam, if there is nothing written, there is absolutely nothing that we can do. Isn't it? You have to try doing something. If you are not able to follow, then you have to reach out and ask. If you don't reach out to us, then we will have trouble. Okay?
Sir, midterm exam results are given, sir, to us?
Yeah, you must have received an email. If some of you have access to the portal, you can log in and check in your portal. For others who don't have access to the portal, will the results will be sent by email. I think one of you have asked Femina, saying that one of the batches does not have access. So Femina will share.
Assignment 1 was given marks, not.
See, midterm marks, I think at 4:42.
Sir, I think
5:42, Femina has sent an email.
yeah, we received email some half an hour back, sir, I think.
Yeah. And Raushan has responded that you guys don't have access to the portal. So she said she will share the things by email. Okay. Any other questions? You are able to see the screen now, right?
Yes, sir.
Yeah.
Yes, sir.
Yeah. So now we have understood how to deal with when you have an effect of mean stress. And so if you carefully observe this problem, with zero mean stress, with 450 MPa, so with zero mean stress, the life corresponding to 542 MPa is 91,716 cycles for 542 MPa alternating stress. That is what it means, isn't it? But if you increase the mean stress from 0 to 200, this 542 has reduced to 450, because at 200 MPa, we can only have 450 MPa stress amplitude. So that is what we are talking about. Is that clear?
Yes, sir.
Yeah. So now, so far what we have looked at is, we talked about the scenario when there is no mean stress. Now we also have talked about a scenario where there is mean stress. But we have always, as we know, in the beginning, we have learned that stress is not a scalar quantity, it's a tensorial quantity. All right. So when I say mean stress, did we talk about which component of the mean stress, or which component of the stress, alternating stress that we are talking about? We did not, because there the assumption is that we were only looking at one-dimensional state of stress. That means there is only one component of stress that is there in the material. But in reality, you will have much more complex scenario. The stresses, sigma xs will be different, sigma yy will be different, sigma zz will be different, tau xy, tau yz, tau xz. All these combinations will be there. Then that means most of the machine components are in general subjected to, particularly if you take shafts are subjected to bending and torsion. Bending gives you, if you only consider bending, it will give you only axial stress. That is more or less uniaxial. So uniaxial state of loading is fine. But A shaft is useless if it does not transmit torque. So if you want to really design a shaft and if you want to transmit torque, it is in general subjected to both bending and torsion, which means you will have the cycling between bending stress as well as torsional stress. That means shear stress. This is a typical classic case of combined state of loading. And all the components in general, 90% of the components will experience this multi-axial loading. Okay. Similarly, cylindrical pressure vessels, they undergo biaxial state of stress. Sigma xx, sigma yy. For example, if you look at hoop stress and longitudinal stress, they are in two different directions. So, although it is purely normal, again they have two principal stresses. But so far we have only talked about one stress. And if you have bending of plates about more than one axis, all these things are classic cases of multi-axial loading. And on the top of this multi-axial loading, if these loads are cycling as a function of time, how do we go about designing such components, right? That is the question that we are asking. Is that clear? So when we look at a multi-axial fatigue loading, let us take the scenario of a pressure vessel, which is subjected to bending, but also internal pressure. If you look at the internal pressure, you have two stresses. One is radial stress, that is sigma P, and then you have longitudinal stress and hoop stress. They vary PR by T and PR by 2T, where T here is thickness. Okay. If that is varying as a function of time, this on the x-axis is meaning you have a pressurized cycle and then unpressuring. So that means sigma P goes from 0 to some value. Then it will cycle like that, PR by T, PR by 2T, sigma x and sigma y. And in this particular case, you don't have shear stress because that is 0. But if you look, if you on the top of that, if you this is PR by T and PR by 2T, and you have a bending moment on this. This is the pressure cycle. I am not talking about the right hand side, I am talking about the left hand side. This is the pressure cycle. If the pressure is cycling like that, then you have sigma 1, sigma 2, two principal stresses, PR by T and PR by 2T. And you have a mean stress My by I, because here Y will be R, so Mr by I. Because there is a mean stress, this mean stress will be there. On the top of that, you have this cycling. Right? So the effective mean stress will be somewhere here. This is a constant bending stress plus this fellow, because this itself is not fully reversed. And hence it is a fluctuating loading. The minimum stress will be Mr by I and the maximum stress will be PR by P or by 2T. Okay. That is in one direction. In the other direction, it is in one direction, it is a fluctuating loading. In the other direction, it is a repeated loading. You can see in the other direction, sigma min is 0. In this direction, sigma min is not 0. So you have a combined cyclic pressure and steady bending. There is a steady bending of thin wall tube. And if you look at this scenario, in this particular scenario, tau xy, shear stress is 0. And if you look at theta p, this is what is the orientation of the principal plane. And in this particular scenario, tau xy is 0. And hence, theta p does not change. It remains constant. So that means the principal directions does not oscillate. Although the stresses are oscillating, the principal plane does not oscillate. It will remain the same. Okay. Now coming to a scenario wherein you have a cyclic pressure. Instead of combined steady bending, let us say you have a steady torsion. So you have PR by TT, PR by 2T. In addition to that, you have a steady torsion. That gives you a shear stress. Because you have shear stress, your principal plane changes orientation because the shear stress is changing. It is constant, but sigma x and sigma y are not necessarily changing, and hence your theta, they are changing in a sinusoidal manner, and hence your theta p is also oscillating. This adds additional complexity because your principal directions are changing. So this case is easy to deal with, and the second case is a little bit more complicated because the principal directions are also oscillating. with each cycle. So then hence this case is more difficult to deal with. Although both of them are combined states of load. So for ductile materials, how do we go about doing it? What you do is, in each of these scenarios, you can calculate sigma 2, what is the alternating stress and what is the mean stress. In the case of in this direction, you can calculate what is the alternating stress, what is the mean stress. Using that, in all the three directions, you calculate alternating stress and alternating stress sigma A1, sigma A2, sigma A3. From there, you compute equivalent stress amplitude, very similar to your von Mises formula. So instead of one stress, you calculate stress amplitude in all the three directions using the principal stresses, principal stress amplitudes, and then calculate the equivalent stress amplitude. And if you are similarly, you can also calculate equivalent mean stress. Okay. Now you can the one way to calculate equivalent mean stress, because your effective mean stress is proportional to hydrostatic stress. So the equivalent mean stress will be equal to sigma m1 plus sigma m2 plus sigma m3. You need not compute equivalent mean stress using von Mises thing, because it is going to be proportional to this. And then you have sigma a tilde and sigma m tilde. And if sigma m tilde is non-zero, now you can use Goodman diagram, extremely very similar. Instead of sigma a, you will use sigma a tilde by SF plus sigma m tilde by SUT is equal to 1 is the formula that you will use. So the mean, whenever you have non-zero mean stress, sigma m, effective non-zero mean stress, sigma m tilde, you will use Goodman diagram. Otherwise, if this happens to be 0, you will use S is equal to a n power b, where S becomes sigma a tilde instead of one of these values. Okay. And this is the simplest implementation, but we are not going into look at very complicated implementation. So let us look at this formula, this problem. You have an unnotched solid circular shaft whose diameter is 50 mm. I am talking about unnotched because when notch comes, things become a little bit more complicated. We will look at the scenario of what happens when you have a notch, very similar to when you have what you call static case. We have to take into account of the stress concentration factor KT, theoretical stress concentration factor. Here also, when you have fatigue, you need to account for the presence of notch. So an unnotched circular shaft diameter is made of the same previous problem, meaning the S is equal to n power b remains the same. A 0 to maximum cyclic torque. That means it is a repeated torque is applied together with a 0 to maximum bending moment. This is also a repeated bending moment. So that means you have a torsional moment, bending, torsional stress and shear stress and normal stress with two cyclic loads being applied in phase. See, whenever there is an out of phase, the situation becomes a little bit more complicated. We are considering the scenario when they are in phase and they are working at the same frequency. How many load cycles can be applied before fatigue failure is expected? Okay. So I would again give you 5 minutes to time to try this problem, and then I will solve the problem. So let's move on, because I think, are you trying, or should I wait for some more time?
We are trying, sir.
Please try. Please try.
Bending stress, I am getting around 61.2 megapascal, sir.
61 or 611?
Yeah, 611.2.
611.2 MPa, and tau
407.4.
407.64.
4 MPa. This is sigma max and tau max, isn't it? Because this guy is cycling between 0 and 10. This is T max and this is M max. So if you would plot the now sigma, this is cycling between like this. And similarly, if you look at tau, like that, right? This is 407.4 and this is 611.2. That is what you have calculated. Now what you need to do, you figure out how. We said R. R is what? R is 0. In the fatigue loading, stress ratio is 0. What is the meaning of that? Stress ratio is nothing but sigma min by sigma max. That implies sigma min is 0. That is why this is 0. So what is sigma A, stress amplitude, and what is stress mean? You have to find out and then talk about it. Similarly, shear stress amplitude, shear stress mean shear stress and mean shear stress.
I can get sigma A as 611.2. Sigma M is 305.6.
Sigma A is what?
611.2 only.
Sigma A is 611.2. What is sigma A? You have to find mean stress, and this is sigma A, isn't it? When R equal to 0,
Okay.
sigma A and sigma M will be same.
Yeah. Then it's divided by 2.
How about shear stress amplitude? That is simply
203.7.
407.4 by 2. That is equal to 203.7 MPa. you need to calculate sigma A tilde and sigma M tilde, right? What did we write sigma M tilde? We said sigma M1 plus sigma M2 plus sigma M3. This is a trace of your stress tensor, isn't it? Tau M is also 203.7 according to our this thing. So if you write sigma A tensor, that will be 305.6 because it's XX, so it's two-dimensional. This is 203.7, this is 203.7, this is 0. Right? Sigma A. If you take sigma M, 305.6, 203.7, 203.70. Right? Because XX, this is sigma A in X direction. Now, sigma M tilde is the trace of that. That means you need not worry about whatever is here. This should be the trace of that. Right? So, sigma M tilde remains 305.6 and sigma A tilde you need to compute. Right? Sigma A tilde, we have the formula, or you can forget, you can try to remember, or you can calculate the way that we have discussed. Equivalent stress, that is sigma XX amplitude minus sigma YY amplitude whole square plus sigma YY amplitude minus sigma ZZ amplitude whole square plus sigma ZZ amplitude minus sigma XX amplitude whole square plus 6 times everything is under root tau XY amplitude square, tau YZ amplitude square, tau XZ amplitude square. The two components are 0, there is only one component. That means 1 by root 2 square root of 305.6 minus 0 whole square plus these two are 0 and 0 minus 305.6 whole square plus 6 times 203.7 whole square. That will be how much? 466.8 MPa. So now you have sigma A tilde is equal to 466.8 MPa. Sigma M tilde is equal to 305.6 MPa. Now our equation sigma A tilde by SF plus sigma M tilde by SUT equal to 1. And you need to find out what is the question. The question asks you how many load cycles can be applied before fatigue failure is expected, right? So again, the same scenario. This is sigma M, sigma A. Instead of now M and M tilde, still this will have to fail at SUT. One point is known. Other point is 305.6 comma 466.8. And now you draw a line. Wherever that line hits, that is my SF. I am calculating my SF, that is sigma A tilde divided by 1 minus sigma M tilde by SUT. Sigma A tilde is 466.8 divided by 1 minus sigma M tilde is 305.6 by 1172. That comes out to be some 631.4 or 5 MPa. So this point is 631.5. Now you have S is equal to 1584 n to the power minus 0.094. Now you need to find out number of cycles to failure is equal to S by 1584 whole to the power minus 1 by 0.094. This is SF. That is equal to 631.5 divided by 1584 whole to the power minus 1.094. What is the value? Number of cycles to failure. Can you check?
17731.
177.
31.
So 17731 cycles, 17,700 cycles. Right? That is the cycle life that the component gives. I strongly encourage you to solve several problems. I will give you assignment number 3 on fatigue failure, whatever we have discussed until now, maybe by tomorrow evening or so. And you can start working on it. It is extremely important that you practice these problems. Okay. This is very application oriented. You should know these principles so that you will be able to apply these things in your work. In several cases, you may have several empirical relations, but where they are coming from is what you are trying to understand. Okay.
Sir, can you go up after sigma A and sigma M? I just want to know how the matrix comes and from there you want to understand.
So sigma A is sigma XX because it's a bending stress. Tau A is tau XY. Right? Sigma MX, sigma MXY. So sigma YY will not be there because it is bending stress, no? Only one plane bending. If you are bending in the other direction, then the sigma YY will come. But it's only one direction bending, so only sigma XX will come.
Okay, sir. Yeah. This is the point I want to. Thank you.
Yeah. Any other questions? So let us try to see what we have learned so far in this course, right? Let us summarize. First, we have looked at SN diagram for fully reversed loading. And we have also solved some problems. Then we have introduced something called correction factors. And then we said, what is the effect of mean stress? All this done for uniaxial loading, right? And then we have said, okay, multi-axial fatigue. And today we have finished multi-axial fatigue, and up to here we only said what is stress amplitude and mean stress, right? Which has an underlying assumption that stress amplitude is constant. Throughout the loading history. But in reality, sometimes the machine components are subjected to this kind of loading. This is what here the stress amplitude is something, here the stress amplitude is something, here the stress amplitude is something. That means sigma A can be varying. You can also, and sigma M as a result also varies. So now that means, so far we have looked at constant amplitude loading. What happens if we have a variable amplitude loading? That is something that we will learn in tomorrow's class. Okay? Is that clear?
Is it minus rule, sir? Actually, minus rule.
Yes, we will talk about Palmgren minor rule. Yes.
Oh.
Any other questions? Okay, if there are no further questions, we'll stop here and then meet again tomorrow. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Sir, one quick question.
Yeah.
Is it possible to share the corrected answer scripts?
Yeah, we have shared the corrected answer scripts also. You can actually look at them. You can check with Femina and Subhalakshmi. Both of them have access to that.
Okay, thanks.
Sure, sir.
Thank you.
And Professor, the marks are out of 50 or is it made
No.
into 100?
No, it is out of 20 or 25. What? No. It is out of 100. She scaled it to 100.
Okay.
Yeah. Okay, bye.